Okay, so we have looked at the list built-in collection type. In this section, week 3, part 2, we're going to take a look at 3 more built-in collection or data types that Python provides, namely the tuple, set, and dict. A tuple is very similar to a list, except that the items in a tuple are contained within parentheses rather than within square brackets. Also, a tuple is immutable. That is, you're not allowed to change the items within a tuple, whereas you can change the items within a list. Here is a tuple that we're creating here on slide 2. T gets 39658. I can determine using the type function that T is, in fact, a tuple. I can access individual, I can display the entire tuple by just typing its name at the shell prompt. I can display an item from the tuple by typing a subscript. T sub 3 is actually the 5, the 4th item within the tuple. A tuple is a sequence like a list, so slices are supported. I can use square brackets with the colon notation to create a slice. Here we're going from item sub 1 up to but not including item sub 3, so that's going to display the 9 and the 6. If I attempt, however, to modify any of the items within the tuple, I will get an error. So if I say T sub 4 gets 17, that is not allowed. So assignment to an item is not allowed to any immutable object. Set is a mutable collection type, like a list. A set is restricted to only having unique values. That is, duplicates are not allowed within a set. A set in Python is like a mathematical set in this way. We define a set by enclosing a sequence of values in curly braces. Here I'm defining S as a set containing 1, 6, 5, 9, 2, 1, 6, 3. You'll notice that I have given some duplicate values in that sequence there. I've got 2 1s, I've got 2 6s. That's okay, but what will happen is that when the set is created, those duplicates are going to be ignored. And the set only contains 1 copy of each of those 6 item values. I can use the type function to see that S is, in fact, a set. The items in a set are stored unsorted. Now, it may appear to you that that is a lie, because here we have S containing, when I display S, it contains 1, 2, 3, 5, 6, 9. But that's just an artifact of the code that creates the set in the first place. We will see, after we look at various more examples, that it's not always going to be the case that the items within a set are sorted. A set provides named operations, similarly to the list data type. Now, since a set is unordered, we don't have the concept of the beginning or end of a set, so we don't have the append function to append an item at the end, and we don't have the insert function to allow us to insert a value at some arbitrary location. What we have instead is the add function that simply adds a value to the set. So let me add 7. And then I can display S, and I see that 7 has been added. If I attempt to add a value that already exists within the set, that's ignored. Discard will remove a value from the set if the value exists. So if I say discard 3, then 3 is discarded. If I say discard 0, let's say, something that's not within the set, that is not considered an error. It's just that nothing happens. Remove is an alternative for discard, which is angrier in some sense. If I try to remove 0, I will get yelled at. I get something called a key error. So discard quietly allows you to eliminate items from the set and just ignores it if you try to remove something that doesn't exist. Remove also removes things from the set, but will complain if you attempt to remove something that does not exist. Here's my set S. Pop will remove and return some arbitrary item. So if I say s.pop, some arbitrary item from the set is going to be removed and returned. I happen to get back the 1. And if I say s.pop again, some arbitrary item is removed and returned from the set. I happen to get a 2. So S has now been reduced to only containing 4 item values, 5, 6, 7, and 9. And I know what you're thinking. You're thinking it looks like pop is returning the frontmost item from the set, but the set does not have any concept of ordering. So the fact that we are getting apparently the frontmost is accidental. You can't count on that being the case. If I want to eliminate all of the items from the set, I can clear the set. And now the set still exists, but it's empty. And to indicate that the set is empty, what's displayed for me here is actually the name of the set construction function with empty parentheses. Okay, S is still a set, but the number of items in S is 0 at this point. Let me recreate my set to contain the values I started out with. I'll just copy and paste these guys. There we go. So now we have some things in S. Since S is a collection, like a list or a tuple, although I didn't show this example with my tuple, I can detect whether a value is in the set by using the in membership test. So 1 in S is true, 4 in S is not true. Let me point out that this also works with tuples. If I say 3 in T, that's true, 4 in T is false. Okay, here on slides 5 and 6 are examples very similar to what I've just demonstrated live. Those named operations that we looked at appended and removed and detected individual items within a set. There are also several named operations that do set versus set comparisons, such as union, intersection, and the like. Let me create another set here. Let's use the example I have on the next slide. All right, so S at this point has 1, 2, 5, 6, 7, 9. Actually, my example on the slide has 3, 5, 6, 7, 9. So let us say S dot discard 1, S dot discard 2. Well, I have to spell it correctly, don't I? All right. So S dot discard 2 and S dot add 3. And now I have got my set S containing the same items shown on the top of slide 8. I'll create another set S2 that has some items with the same value, but also items with different values. 3, 4, 8, 9. Well, actually, it doesn't matter what order I type these in. 10, 9, let's say. And here's S2. So now I have two sets that have some identical items. 3 and 9 exist in both sets, but they also have some different items. 5, 6, and 7 are only in S. 4, 8, and 10 are only in S2. If I say, let me go back to the previous list of named operations. If I say S.union of S2, This does not modify either S or S2, but what it does do is it constructs a new set that is the union of these two sets, and so it's going to contain 3, 4, 5, 6, 7, 8, 9, 10. Now, I did that in order. In real life, we know that sets are not necessarily ordered, but it was just simpler for me to describe that way. And there we are. So 3, 4, 5, 6, 7, 8, 9, 10 is the union. Now that, as I said, it didn't change S, it didn't change S2. If I wanted to save that union as a set, I should create a variable to refer to that newly created union. All right, so S3 now refers to a newly created set that is the union of S and S2. S dot intersection of S2 is the items that are common to both. So this will only be the 3 and the 9. S dot difference with S2 is going to give me back, in set notation, S1 minus S2, which means the items that are in S1 but that are not also in S2. All right, so the items that are, well, okay, so they're called S1 and S2 on slide 7. Here in my examples, I have S and S2. So S contains 3, 5, 6, 7, 9. S2 contains 3, 4, 8, 9, 10. The items that are common are 3 and 9. So when I say S minus S2, what I'm going to get is the values in S that are not also in S2, which is just going to be the 5, 6, 7. Now, on the other hand, if I say S2 dot difference S, I get the items that are in S2 but not in S, and this is going to be the 4, 8, and 10. Now, notice, at long last, we have come across an example where the order of the items in this difference is not ascending. Okay, so we do have the correct items in this difference, 4, 8, and 10, but they are not shown in some kind of ascending order. The symmetric difference is the items that are in one set or the other set, but not both. So in other words, the symmetric difference ends up being the union of these two differences. Let's try that. S dot symmetric difference, S2, is 4, 5, 6, 7, 8, 10. That does happen to be shown in order, but again, that's just an artifact of how it's implemented. I can ask whether one set is a subset of another set. Okay, so I've got this thing S3 sitting around, which is the union of S and S2. If I ask whether S is a subset of S3, of course that had better be true. If I ask whether S is a subset of S2, that is not going to be true. In addition to these named set versus set operations, there are also symbolic operations that I can use as an alternative. For example, the ampersand is used as an alternative for intersection. And you can think of the ampersand as meaning and. So if I say S and S2, that's going to give me the items that are in S and also in S2, which is the intersection of the two sets. The vertical bar I can think of as meaning or. If I ask for the things that are in S or in S2, that of course is the union of the two. Now, exclusive or, the caret symbol or the hat or the circumflex, there are many different names for that character. The exclusive OR of S and S2 is the same as the symmetric difference. That is, it's the items that are in S or in S2, but not in both S and S2. All right, so the items that are in S but not S2, and or combined with the items that are in S2 but not S. And you can see that's the same as what we got for the symmetric difference up here. And we can use a minus sign for just plain difference. So S minus S2 is the same as S dot difference S2. Okay, so here on slide 10 we have examples similar to what I've just demonstrated live. I just want to show this final one here. S or S2 is the union of S and S2. That turns out to be equal to the items that are in one but not the other, the exclusive OR, union the items that are in both. Okay, so S XOR S2 is the items that are in S or in S2 but not both. S intersect S2, S and S2 is the items that are in both. Okay, so the items that are in one or the other but not both, union the items that are in both, of course, has to be the items that are in one or the other. So this is going to give me true. Any kind of identities or comparisons that you can do with mathematical sets, you can also do with Python sets. You obviously just have to know the notation. One restriction on the items that you can put into a set is that these items have to be what's called hashable. That is, it has to be possible to tell one value apart from another value, and the values cannot change over time. For example, low-level objects like int, float, stir, bool, and the single value none are hashable. Likewise, an immutable value, for example, a tuple is hashable if all of the items that the tuple contains are also hashable. However, a list is not hashable because it is possible to append items to a list, to remove items from a list, to change items within a list using subscripts and an assignment. Similarly, a set itself is not hashable for the same kind of reason. Therefore, a set cannot contain a list. It cannot contain a set. It also cannot contain a tuple if the tuple contains something like a list or a set. Here's an example of a set, S3, that contains several different types of items. It contains the int 5, the float 4.7, the single value none, a tuple containing two stirs, so that's hashable because the stirs are not mutable. We also have the stir hello and the Boolean value true. When we display S3, we may or may not see the values in S3 displayed in the same order in which those values were defined. A fourth kind of built-in data structure that Python provides is something called a dict or dictionary. It is mutable. That is, you can add things to the dictionary and change things within the dictionary. Unlike the list or the tuple or the set, each item in a dict has two parts, two components. There's a key and a value associated with that key. When you put elements into a dictionary, you use a colon to separate the key from the value. Like a set, we use curly braces if we define a dictionary manually. We just need to remember to use the colon character to separate the key from the value in each item that we add to the dictionary. There are restrictions on keys, which are basically the same as the values that you can store in a set. That is, each key has to be unique within the dictionary, and keys have to be hashable. But there's no restriction whatsoever on the values associated with those keys. The values may be the same as each other, they may be different from each other, they may be of any data type, they may be immutable or mutable, doesn't matter. In this particular example, I'm defining a dictionary, N2E, standing for name to email, and the first item in this name to email dictionary has the key John, that's some user's name, and then the value associated with that key, jkostlund@gmail.com. Well, I cleverly hit the enter key instead of the single quote. So let me copy and paste this and try again. All right. Okay, so there is the first item in this dictionary, N2E. The key is John, the value is jkostlund@gmail. In this case, both the key and the value happen to be strings. Since I'm using curly braces here to contain the items within the dictionary, Python will be okay if I just hit the enter key and continue typing on the next line down. So my second item is going to be al as the key with al@alcorp.net as the as the value. All right, so we start seeing the danger of typing long chunks of Python code interactively at the shell. All right, so there's my second value, and I'll type in the third value and get back to you in a moment. All right, so now I've typed in the third item and hit my curly brace. I have not yet hit the enter key. So N2E is the dictionary that I'm creating. The first item has key John, value jkostlund@gmail. The second item has key al, value al@alcorp. The third item has key Bob, value bob@bsoch.net. There we are. So I can use the type function to discover that N2E is a dictionary, and to access things within the dictionary, I can use square brackets, but instead of using an integer subscript as I would within a list or a tuple or a string, for a dictionary I use a key as a subscript. So if I give the key John in square brackets, that's going to return to me the value associated with that key. And if I use the key Fred, well, there is no item that has a key value of Fred. So in this case, I'm going to get an error. I get a key error telling me that Fred is not a key in this dictionary. I can add an item to the dictionary easily by using the subscript notation with a brand new key, but I also have to assign a value to be associated with that key. So here I'm creating a new dictionary key, sci, and sci@new.edu is the value associated with that key. If I now display N2E, I will see that the keys, John, Al, and Bob, are still here, and I've got a fourth key, Sci, with Sci's email address as the value. It is a feature of the current Python release, Python 3.7, that items within a dictionary are stored in the order in which keys are created. So John is the first item, Al is second, Bob is third, Sci is fourth. In addition to being able to add a new item to the dictionary, I can also use the subscript or lookup notation here with assignment to change the value associated with a certain key. So here, the original value associated with the key John was jkostlund@gmail.com, which is a valid email address for me. But perhaps I want to change that to my official Andrew email address, and so this statement does that. Ente sub John is now going to be jostlund@andrew. And we see that ente has been modified. Here's the new value associated with the key John. But notice that the order of the keys has not been affected. All right, so the order of the keys is the same as it was before. Like list and set, dict has many named operations. For example, get is another way of looking up the value associated with a certain key. But unlike the square bracket notation, get will not raise an exception if the key is not found. For example, if I say ente sub Dave, I do get an exception, a key error. But if I say ente.get Dave, that's actually going to return none without throwing an exception. And as we know, none does not get displayed by the shell, so it appears to me as though nothing had happened. If I wish, I can specify a default value to be returned, so I could say something like ente.get Dave, and then as a default I could say Dave's not here, and I get Dave's not here as the result of that, because Dave does not exist within the dictionary. Pop item will return the item with the most recently added key as a tuple. That is, what I'm going to get back is going to be contained in parentheses with the key and then a comma and the value. Let's try that. So here's ente again, and the last key that I added to ente was psi. If I say ente.pop item, I will get that item whose key is psi and whose value is psi@nou.edu. Not only does that return that item, but the item is now gone from the dictionary. I can use clear if I want to eliminate all of the items from the dictionary. Let me do that just for chuckles. ente.clear clear ente.clear. Now ente is empty, and an empty dictionary is just indicated by open close curly brace. It is still a dictionary, but it has no items in it, therefore its length or its size is 0. Let me restore ente to contain some values. I'm just going to copy and paste what I had up here. Okay, so now ente is back containing some values again. Here on slide 17 are similar examples to what I've shown. A dict is iterable. In fact, a dict can be iterated through in many different ways. The dict itself, if I say for val in ente, the dict itself is iterable, and by default what you get when you iterate through the entire dictionary is just the keys. All right, so I'm saying for val in ente, the dictionary, and val gets set to each of the keys one at a time. As an alternative, to be a little more explicit, I can say for val in n to e dot keys. That accomplishes the same thing. Or if I would rather iterate through the values instead of through the keys, I can say for val in n to e dot values. Notice that the values come out in the same order as their corresponding keys. So the first value I get out is the value associated with John. The second value I get out is the value associated with Al, etc. Pop item, you may remember, returned to me a tuple. So when I said n to e dot pop item up here, I got a tuple in which the sub 0 item is the key and the sub 1 item is the value. I can iterate through the entire dictionary, obtaining all of the items as tuples without removing them from the dictionary by saying for val in n to e dot items print val. All right, and so that is a convenient way of iterating through the key value pairs within the entire dictionary. Here in slide 19 are examples very similar to what I just demonstrated. All right, so we define a set by specifying the individual values that go into the set. We said something like S gets 1, 2, 3, 4 in curly braces. Similarly, if we want to define a dictionary, we say curly brace and then key colon value. We use curly braces in both cases, is what I'm saying. So S is now a set of 4 items. D is a dictionary of 2 items. The first item has key 1 and value 3. The second item has key 2 and value 4. An empty dictionary is, as I mentioned before, just the empty parentheses. All right, so that thing is an empty dictionary. It is a dictionary. It is empty. Whereas an empty set, we can't use the curly braces to create an empty set. So what we do is we use the set construction function with no argument. If I then display SE, it displays as the set construction function with no argument. The type of SE is set, and the size of SE is 0. So this is a sort of a little language wart to keep in mind, which is that both dictionaries and sets use curly braces, and consequently you have to differentiate an empty dictionary from an empty set by using the curly braces for a dictionary and the set construction function with no argument for a set. This is not my fault. I did not do that. Okay, now if you want to create a one-item set or a one-item dictionary, then you can go ahead and use a curly brace in both cases. There's no possibility for confusion because a dictionary has to consist of both a key and a value. So here is a one-item dictionary with the key 4 and associated value 5. D1 is, of course, a dictionary. The size of D1, the length of D1 is 1. S1, I can say curly brace 4, let's say. All right, and so now S1 is a set, and its size is 1. Okay, so differentiating between an empty set and an empty dictionary is the only peculiar case. Okay, so we now know about the 4 built-in data types or collection types within Python: lists, tuples, sets, and dicts. Between these, you can manage data in a very powerful and flexible way. Okie dokie, so that is it for week 3.